context-debloating approach for object-sensitive pointer analysis.
Hello, everyone. I'm Dongjie, come from the University of New South Wales. In my presentation, I will introduce a new context-debloating approach for accelerating object-sensitive point analysis. We know programs writing in C, C++, and Java are usually full of pointers and references. And point analysis answers the following two problems. One, what memory locations can a pointer point to? And two, whether two pointers could be aliases. Point analysis is the foundation of many static program analysis, like compiler optimization, code construction, and so on. It has many implementations in many popular frameworks. In our paper, we focus on object-sensitive point analysis. Object sensitivity is an effective technique in improving the precision of Java point analysis. In object sensitivity, the context elements of the context are receiver objects of some methods. Here is an example of the context in object-sensitive point analysis. Here, the K is the maximum number of context elements in a context. Here is an example. In this code snippet, you can see the other method of the hash state is invoked twice in line 3 and line 4. With two different receiver objects, S1 and S2. So the other method has the receiver object of the other method has two different receiver objects. So the context of the other method will be analyzed in two different contexts, S1 and S2. Generally, when we increasing the K, we can improve the precision of the object-sensitive point analysis. But it can also make the point analysis inefficient or even unscalable. As you can see from this figure, the analysis time of a program called the Index increases exponentially as the K increases. So the reason is that the context of object-sensitive point analysis will grow exponentially with K. Suppose this code snippet is analyzed in different contexts, then the other method of the hash state will be analyzed 2n times in 2n different contexts, S1 CI and S2 CI, where the I could be any number in 1 to n. To address this exponential explosion problem, in my previous publication, I proposed a novel technique called context-debloating. Let's briefly review the key idea of context-debloating. In K object sensitivity, the context elements are objects. And in a program, some objects are context-dependent and others are context-independent. Here is an illustration of whether an object is context-dependent or not. Briefly speaking, an object O is context-dependent if analyzing it context-insensitively in kobj. It will cause some program variables to lose precision. The key observation behind the context-debloating is in the real code, most objects are actually context-independent. For example, in this code snippet, the object S1 and S2 are created and used locally and are independent of the calling context. So align context combinations on this object only increase analysis time without any precision benefit. So the key idea of the context debloating is inhibit the context combination on context independent elements. Given the fact that the S1 and S2 here are context independent objects, so we can inhibit the context combination shown in the dotted lines. So the context of the other method will decrease from 2n to 2, which will make the point analysis very efficient without any precision loss. But the challenge in context debloating is how to precisely identify context-dependent and context-independent objects. In our previous publication, we proposed a context-free language-based approach, which is theoretically undecidable. And the eagle approach, which over-approximates the context-free language, will select almost all non-trivial context-independent objects as context-dependent objects, making the technique less efficient in practice. In the prior context-debloating approach called the Conch, we approximate the context-free language with 3 linear verifiable conditions. Although it is already very efficient, it is field insensitive, which limits further performance improvement. So in this work, we introduced another context-debloating technique called DebloaterX. Our technique is one limited field sensitive and could significantly improve the performance with negligible precision loss. Our approach identifies context-dependent objects by usage patterns. We believe that the usage patterns of context-dependent objects in the real code are finite. And we have summarized the following 3 patterns. I will introduce these patterns later. And our evaluation shows that the 3 patterns are enough to preserve 99.8% of precision in the real-world programs. From this slide, I'm going to briefly introduce our approach. Here is the overall algorithm of the context DebloaterX. It consists only 3 steps and is conceptually very simple. In step 1, given a program P, we first collect container objects in the program. And in step 2, for each container objects, we check whether their usage pattern belongs to any predefined usage patterns. If yes, we will select it to be context-dependent. And in step 3, we will return all the context-independent objects to the main point analysis for context debloating. We first give the definition of the context container objects. An object O is a container object. It must have at least one point field F, and there is an incoming value flow that is stored into O.F, and an outgoing value flow that flows to the outside of the object. As you can see from this figure, we have made an approximation here. We only differentiate one field F and do not care about the other field access path that is longer than the field. So the 2 field access paths in the 2 yellow boxes are aliases in our module. Here is an example code. In this code, the hash set object created in the line 1, marked it as S1, is a container object. Because you can say it has a field map defined in line 5, and an incoming value flow in the other method from the parameter P and stored into this dot map. And an outgoing value flow in the iterator method from this dot map to the return variable and flow out of the method. Here are the rules for identifying the container objects. To compute the incoming and outgoing value flows, we have designed two DFAs. As you can see from the red circles, the DFA differentiates a specific field F. Thus, it is one limited field sensitive. From this slide, I briefly introduce the three use patterns. The first pattern is the inner container pattern. Container object is an inner container if it can be accessed by the out container via a field and could be used by the out containers for storing and retrieving data. As you can see from this example, the hash map object created in the line 4 is associated with this out container via this dot map and is used for storing and storing data in the other method and used for retrieving data in the iterator method. Inner containers are context dependent because they need to distinguish the data stored by their different out container objects. The second pattern is factory created containers. They are usually created in a static method and directly returned in the method. Factory created containers are context dependent because they need to differentiate the data coming from the different calling contexts. And the third pattern is called the container wrappers. Container wrappers in the real code are usually iterators and enumerators. They are usually created in an instance method and directly returned. And their contents are usually come from the method where the objects are created. The container wrappers are context dependent because they need to differentiate the wrapper contents from the different calling contexts. This slide just shows the rules for identifying the patterns. Here is the workflow of our DebloaterX guided K-object-sensitive point analysis. We first use a context-insensitive point analysis to analyze the program. And with the imprecise points to information, the DebloaterX will select a set of context-dependent objects based on the three usage patterns. And finally, the context-independent objects are returned to the main point analysis for context debloating. Our approach is built on top of the Qilin framework, and the source code and the artifacts are publicly available. Here are this slide shows the benchmarks, settings, and metrics used in our evaluation. The benchmarks are from the two different versions of the couple benchmark, and so they are very representative. Our evaluation finds that averagely in a program, about 26.7% of objects are container objects, and only 7.6% of objects are context dependent. The ratio of context dependent objects identified by the three patterns are respectively 4.8%, 1.2%, and 1.7%. The objects identified by the inner container pattern and the container wrapper pattern has a small overlap, but not that significant. Our approach could speed up the K object 19.3 times when K equal to 2, and 150 times when K equal to 3. Comparing with the state-of-the-art approach enables kobj to run significantly fast and achieve better scalability. In terms of precision, our approach loses less than 0.2% of precision, which is very close to that of Conch, and is more precise than Zipper. In summary, this paper introduced a new context debloating approach, DebloaterX, based on three container usage patterns. It enables K-object-sensitive analysis to be more efficient than the state-of-the-art while preserving nearly all of the precision. There's still some work to do in the future. First, we plan to investigate the performance issues on extremely large programs such as the Eclipse. And we also want to develop context-debloating techniques for other kinds of context sensitivity, like cosine sensitivity. That's all for the presentation. Thanks.
Questions?
Okay, this is amazing how much you debloated. Do you think you could use the same technique to debloat in functional programs?
It's only for object-oriented programs.
But you might identify patterns in functional program that match the patterns from the object world.
Because we only designed the approach based on the object sensitivity, and object sensitivity is currently only very efficient for object-oriented programs.
Okay.
Yeah.
Do you think that there are other object patterns that you're missing that might help with debloating Eclipse? Or what's the slowdown in Eclipse?
Basically, the current 3 patterns is very precise to preserve the precision of the Eclipse benchmarks. But there are still about 200 objects that are mistakenly identified as context-dependent objects, but they are actually context-independent. So this set of objects hurts the efficiency of the analysis. So we still could not analyze these objects scalably. Right.
Thanks. Okay, why don't you get it set up? I had one more question.
Okay.
While he's setting up, so sorry. You showed experiments analyzing against Jerry 1.6 and 1.8, I think is what you showed. And Java 21 was released a few weeks ago. So do you have any idea what happens with more recent Java versions? Are there new analysis challenges that we need to be tackling in order to analyze against more recent standard libraries?
We actually plan to extend the Qilin framework into the SuiteUp framework so that we can support more features in the most recent version of Java programming languages. Yeah, thanks.
Okay, let's thank the speaker again.